In this chapter, we're going to look at conjugated pi systems. We'll start off examining how these systems work, what sort of properties they have, and look at some reactions involving them. And we'll close out the chapter looking at UV-Vis spectroscopy. So to understand what I mean by a conjugated pi system, let's look at dienes in general. All right, now a diene, as the name suggests, is two alkene functional groups, two carbon-carbon double bonds that are found in your molecule. Now, where those double bonds are in relation to each other gives us those different categories. We have cumulated dienes, where the two sets of double bonds have a carbon in common. All right, so the pi bonds are adjacent to each other. You can have isolated dienes where the double bonds are far apart from each other, completely unrelated to each other. They just happen to be in the same molecule, but otherwise they're not related. The conjugated setup is the one we're going to examine quite a bit in this chapter, and you'll see why in a second that it's pretty interesting, all right, in terms of just the way the electrons are set up and the resulting properties that arise from that. Now, for this conjugated system, you have a single bond in between your two double bonds. All right. Now, to understand why this is special, look at the hybridization of each of the atoms involved here. All right. Now, you need an unhybridized p orbital in order to form each pi bond that's involved here. And in the case of your accumulated system, while your carbons on the outside of the system are sp2 hybridized, that middle carbon is sp hybridized. All right. In your isolated system, of course, you have sp2 hybridized carbons here and here, but you have an sp3 hybridized carbon in between them. In the conjugate system, you'll see that all of the carbons in that system are sp2 hybridized. All right, so sp2, 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 sp2. Okay, and that's where this the interesting stuff arises. So if you want a visual of that, and it kind of helps you understand why some of the properties we're going to see arise here, look at the p orbitals involved in those carbon atoms. All right, now in the case of your accumulated system, of course, because that middle carbon is sp hybridized, you have one set of unhybridized p orbitals involved in the pi bond on the left, and you have another set involved with the pi bond on the right. Okay, so the two pi bonds are perpendicular to each other, in other words. All right. In the case of an isolated system, of course, you have your regular pi bond with your overlapping between the unhybridized p orbitals, but of course you've got that sp3 carbon in between, and so these are just two isolated pi systems, hence the name. Now look at the conjugated system. Because of all of your carbons being sp2 hybridized and all of them having that unhybridized p orbital, notice how they line up like this. Now, when we draw this out as a regular Lewis structure, we don't really show any connection between these two p orbitals. We just show this as a single bond between these two carbons. But the fact is, it is possible to have all four of your unhybridized p orbitals in the same phase. Okay, they could theoretically overlap with each other, and this is where the sort of specialness of this system arises. Okay, so as I mentioned, this chapter will focus on conjugate systems. We're going to look at systems where we have these strings of sp2 hybridized atoms, and we're going to see, again, the properties and reactions of these systems. Now, in the examples we looked at carbon-based dienes. So, basically we had two sets of double bonds with 4 sp2 carbons. Now, that need not be the case. We could have heteroatoms. You can see here that we have an enone, and that means we have an alkene and a ketone, hence the ene and the one part of the name here. And they're also conjugated here. Okay, notice that these 4 atoms are all sp2 hybridized. All right, and there's your 2 double bonds between those 4 atoms. Likewise, you don't necessarily have to limit yourself to a diene. Look at this system over here and see if you notice how far that conjugated system extends. Okay, so hopefully you've started to notice that if we count all these carbons, including this heteroatom here, this nitrogen, we have sp2, sp2, and so on. It goes 1, 2, 3, 4, 5, 6, 7, 8. So we've got all 8 of these involved in one pi system. All right. Now you're probably saying to yourself, what about these 2 carbons here? These two, this double bond here is isolated. Notice the sp3 hybridized carbons that are in the way. Okay, so this is not part of that conjugated system. All right, so if you want a visual again of all the p orbitals here, you can see how these are all in a string together, but these 2 over here, that's representing these 2 carbons here, are kind of isolated because of these sp3 carbons that kind of block them off. All right, so let's start off by looking at how we can make these dienes, right? How do we make these conjugated systems? We've seen that we can form carbon-carbon double bonds. We can form alkenes through elimination reactions. Now, depending on where you want your double bond, which is kind of important here, we want to have this conjugated system, we want to control the regiochemistry of our elimination reaction. All right, so we're thinking here between the Zaitsev versus Hofmann product. So in this scenario, we want to make the Hofmann product here. All right, the Zaitsev product would form a double bond over here, which would give us the accumulated diene. So to make the Hofmann product, which would give us the conjugated diene, notice that we need to use a bulky base. All right, so think back to elimination reactions in last semester, or if you're struggling to remember that stuff, definitely brush up on that a little bit, before coming back here. But that's basically how we would make our diene. And of course, here with our dihalide, we can use 2 equivalents of that and just make the diene that way as well. Okay. Now let's look at some of those properties that we're going to observe in these conjugated pi systems. So in general, you know that a single bond is going to be longer than a carbon-carbon double bond, right? That being said, the carbon-carbon single bond that we observe in a conjugated pi system is shorter than we would expect. Okay, now the reason for that is because, as I mentioned earlier, that single bond, even though we draw it as a single bond in our Lewis structure, it has some double bond character to it. Okay, those carbons are both sp2 hybridized, and that affects the that orbital that's involved in the in the overlap forming that sigma bond matters. The smaller size of that orbital causes the bond length to be shorter as well. Okay, so you can see if we compare sp3 versus sp2 orbitals, an sp2 orbital has more s character than an sp3 hybrid orbital. Okay, and of course s orbitals are smaller than p orbitals. All right, so let's have a look at the stability that we get out of these conjugated dienes. Now, if you recall from last semester, the way we can figure out stability when comparing alkenes is to compare heats of hydrogenation. All right, so you've probably recognized this technique in general. I think we kind of did this with heats of combustion as well for alkanes. And so in general, looking at the heats of reaction for certain types of reactions, you can kind of get a feel for how stable your your reactant is, because the less stable it is, the higher in potential energy it'll be, and therefore the greater heat is released when it reaches that more stable product. All right, so when you're comparing your enthalpy of whatever reaction, in this case hydrogenation, typically the larger the enthalpy, the less stable your original chemical. Okay, and vice versa. If it's a smaller amount, that means it was more stable to begin with, and that's why it released less energy when it formed the more stable product. Okay, so here's that comparison. So if we compare a regular alkene here, and then we compare a corresponding conjugated diene, notice that there is a 15 kilojoule gap in energy. All right, when we look at their respective heats of hydrogenation to make the corresponding alkane. Okay, so with that in mind, let's see if we can organize these in order of stability. So we've seen that conjugating pi bonds increases stability. So let's see if we can rank these. So pause this video and take a second and try and rank these out. Okay, so if you're back with us, here are the answers. And basically, you want to look for these conjugated pi systems, right? So in the case of A, notice that these two pi bonds are completely isolated. We've got sp3 hybridized carbons in between them. They're not conjugated at all, right? So that's why A is the least stable out of all of these. Now, if we look at the other examples, notice that we have conjugated systems. So here we have these two, these two double bonds are linked together by 4 sp2 hybridized carbons. So we've got a system of 4 carbons there. Likewise, here's another system of 4 carbons. Okay, and in both cases, we have a third double bond that's isolated from the others. Now, look carefully at D. Here we have 1, 2, 3, 4, 5, 6. All right, notice that all of these carbons are sp2 hybridized. Okay, so all of these are linked together. So we have 3 pi bonds with 6 sp2 hybridized carbons together. So that's why D is the most stable. It has the largest conjugated system. Now, what's the tiebreaker between B and C, right? Why is B listed as more stable than C? To see that tiebreaker, you've got to go back to last semester where we looked at alkene stability in general. Remember, the more substituted your double bonds, the more substituted your alkene, the more stable it's going to be. So if you're having trouble seeing this, my advice is to label the substitutions on each of your double bonds. So for example, this one is tri-substituted, right? We've got 1, 2, 3 carbons coming off of it. This one's tetra-substituted, okay? Of course, this isolated one over here is di-substituted. Now if we look at these 3 over here, if we look at the conjugated system, this double bond is di-substituted, this double bond is tri-substituted, and that isolated system is also di-substituted. So notice that just having that tetra-substituted and tri-substituted, or I guess primarily that tetra-substituted double bond over there makes B more stable. All right. Now, normally when you think of single bonds versus double bonds, one of the key properties we learned early on with alkenes is that you can't rotate carbon-carbon double bonds, right? That pi bond's kind of locked in place and stops you rotating around that double bond. They're kind of fixed. However, we know that single bonds in general are free to rotate, right? Now, what when it comes to these conjugated dienes, however, remember that carbon-carbon single bond in the middle of that conjugated system is a little bit special. It's a little bit different from your typical carbon-carbon double bond, single bond, in that it has some double bond character to it. Okay, so while single bonds normally can freely rotate, it turns out that the quote-unquote single bond of our conjugated system actually does have an energy barrier to its rotation. Okay, so you can actually get locked into either a cis or trans format where it's your double bonds that are on the same side or on opposite sides. Okay, so unlike your typical alkene where you use cis and trans to denote the substituents coming off the double bond as being cis or trans, here we're looking at the double bonds coming off of our single bond as being cis or trans. So to designate that, we put an S in front of the designation, right? So we say S-cis when we have both of these double bonds on the same side of that single bond in between them. Likewise here, with the double bonds on opposite sides of that single bond, it's S-trans. Okay. In both cases, of course, you have that overlap of of unhybridized p orbitals, but of course then you have to consider sterics too. Right, so with the S-cis conformation, just like with a regular cis alkene, there's some steric hindrance there. However, when we start looking at pericyclic reactions later on, you're going to see that there are certain advantages to having an S-cis system. Basically, it makes certain reactions possible, from an electronic and a steric standpoint. All right. So to illustrate that, here we can see the energy values of our different conformers. And again, as I pointed out, that trans isomer is going to be more stable sterically, and therefore it's lower in energy. Here we can see that energy barrier to that rotation. So notice that both of your conformers have that overlap of p orbitals. We have to break that conjugation in order to rotate around that carbon-carbon single bond, and that's why we have an energy barrier here that we've got to overcome. Okay, so that, if you want to see what that looks like, you can see here as we rotate around that single bond, notice that we no longer have overlap between this p orbital and this p orbital here. Okay, now to understand a lot of this stuff, it helps to be able to go back to molecular theory and quickly just sketch molecular orbitals, right? Again, I'll show you how to do this relatively quickly and easily. This doesn't have to be a very drawn out process. We kind of want to see the frontier orbitals. That's where all the interesting chemistry happens, right? That's where our reactions take place, at those highest occupied and lowest unoccupied molecular orbitals. All right. So when it comes to drawing molecular orbitals, right? So think back to where molecular orbitals come from. They arise from your atomic orbitals. Now, we're really concerned about those p orbitals. So we're just going to focus only on the p orbitals, and we're only going to look at the resulting pi bonds that form. Okay, so we're drawing very simplified molecular orbitals here when we start examining this stuff. Okay, so let's look at a really simple example here to jog our memories on how molecular orbital theory works. Let's say we have ethylene, or ethene if you want to use the IUPAC name. Okay, so we've got two carbons, and each of those carbons is sp2 hybridized, so they have an unhybridized p orbital, right? They have a 2p orbital that's going to be involved here. So if each of your atoms, each of your carbons contributes one p orbitals, we draw them on either side here as atomic orbitals. Now, they're the same energy, right? Because they're both identical p orbitals. But when they form molecular orbitals, we get the same number of molecular orbitals, but they're going to be at different energies. We get a bonding orbital, which is more stable and therefore lower in energy, and we get an anti-bonding orbital that's going to be higher in energy, okay, because it's less stable. Now, what causes that stability? The phases of your p orbitals can be either in phase or out of phase. All right, so when they both of your p orbitals are lined up, all right, so if you were drawing your individual p orbitals, here's kind of what that would look like. So, right, so here's our p orbital, and it looks like this. Okay. Likewise, here's another p orbital on this carbon that looks like this. If both of these were lined up, so we had one, the same phase pointing upwards, okay, we would have an overlap between those two, and that's where this bonding orbital comes in. This is basically your pi bond, all right? So this is a pi bonding orbital. Oops, that's a horrible Greek letter pi, but okay, there we go. There's the letter pi, and that's our pi bonding orbital. Now, here I've drawn them with the same phase, but let's say this one was in the opposite phase. This was pointing downwards like this, okay? So instead, we have this setup here. Now, this and this do not overlap. So we have a node here between them, okay? A place where there is sort of no overlap, no electron density, okay? And this is our pi star, or pi anti-bonding orbital, okay? Notice that our lowest energy orbital has no nodes, right? There's a complete overlap between everything. Everything's in the same phase. As you go higher one step in energy, you add one node. Okay, and we'll notice that trend as we start adding more and more carbons. So, let's try adding more and more carbons. Let's say we had 1,3 butadiene. All right, so we have 4 carbons connected together, right? And we're trying to make this conjugated pi system. What do the different molecular orbitals look like, and how do we sketch them out? You can just draw them in a simplified manner like this. Just draw the p orbitals, as I've drawn here, and ask yourself, what combinations can we have of these atomic orbitals to give us our different molecular orbitals? All right, we know our lowest energy one will be where all of these are in the same phase as they're drawn here. Okay, so we have this complete overlap, and that's what that lowest energy pi bonding orbital is going to look like. Okay, and if you want to see what that looks like kind of in real life, this is what that molecular orbital looks like. Now, as you go up in energy, right, we have 4 p orbitals here, so we're going to have 4 molecular orbitals that we're going to draw out. Each time we go higher in energy, we're going to increase the number of nodes. Okay, so our lowest energy one has no nodes. There's a complete overlap between everything. Then we go to 1 node, 2 nodes, and 3 nodes. All right. That highest energy orbital is where everything is not going to overlap. There are nodes between all of your orbitals. So that one's pretty easy to draw as well, right? You just alternate the phases of your p orbitals, okay, and you have no overlap. In between, you've got to kind of figure out what things look like. So here with 1 node, you know that 1 node's going to be in the middle here. Okay, so we have overlap on the left, we have overlap on the right, but there is not overlap in the middle. So these have to be in opposite phases. Okay, for here where we have 2 nodes, we have overlap in the middle, but notice the phase change on the outsides. Okay, so that's where we have a node over here and a node over here. Okay, here a node, there a node, everywhere a node. Anyway, moving on. Oh, quick point actually, though, before I move on. Notice where the electrons are going. I think I forgot to remind you of this when we reviewed it with ethylene here. Notice that each of your carbons is contributing an electron, and so both of them go into that pi bonding orbital, right? So that's why this molecule forms very readily, right? And this is a stable molecule that forms. Those electrons go into that bonding orbital. Likewise here, out of the 4 electrons contributed from our 4, sp2 hybridized carbons, notice that 2 of them go into each of our pi bonding orbitals, and our anti-bonding orbitals are empty. Okay, and again, this is why 1,3-butadiene is a stable molecule that forms. So again, if we examine those occupied, those pi bonding orbitals, we can once again see where some of that partial double bond character goes. So we can see why that middle bond, even though our Lewis structure draws it as a carbon-carbon single bond, which we kind of see over here, we see why there's that partial double bond character. Okay, one of those occupied molecular orbitals has, it has that overlap between p orbitals, which we see as a double bond. Okay, yeah, so that's why we typically see that middle quote unquote single bond seems a little bit shorter and stronger than your typical single bond. It seems a little double bond-ish. And of course, you can scale this up accordingly. So here we have 135 hexatriene. So we've got 6 carbons in our molecule, and so we draw our 6p orbitals in our conjugated pi system. And just as with our previous example, we can scale up our number of nodes as we go along. So we start off with our lowest one where everything's overlapping. Then we have 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, right? So you'll have n minus 1 nodes. That's your, the maximum number of nodes you can have, and that's your highest energy pi anti-bonding orbital right here. Okay, a little terminology I alluded to earlier. I mentioned the terms HOMO and LUMO, and I said these are frontier orbitals. These are the ones that are really important that we pay attention to. What did I mean by HOMO and LUMO, or highest occupied molecular orbital and lowest unoccupied molecular orbital? Well, they're frontier orbitals because they're the border between occupied and unoccupied orbitals. So here, this is the highest energy occupied orbital. So this is our HOMO. Okay, it's the highest occupied molecular orbital. Notice it has electrons in it, and it's the highest energy out of all the ones that do have electrons in them. Over here, right next to it, just higher in energy, is the LUMO. This is out of the 3 orbitals that are unoccupied, that are empty, that don't have electrons in them. This one's the lowest in energy. So if there's any chemistry going on here, if you're going to destabilize these bonds, you're probably going to push an electron from here into here. Okay, and that's probably how you're going to start any reactions involving this conjugated pi system. So again, that's why these frontier orbitals are kind of important. Okay, so here's an example of that, right? One way you could promote an electron is to shine light on it, right? You provide the energy required to overcome this energy gap here. You can provide that using light. Okay, so using photons of the necessary energy. Okay, please note that when we do this, by promoting an electron up to what used to be the LUMO, this now becomes the HOMO because it's occupied, it's got an electron in it. So that is now the highest occupied molecular orbital. Okay, and the orbital above it becomes the new LUMO. Okay. All right, so by the way, if you ever want to measure that energy gap, as I mentioned, that energy gap will correspond to the photons of light that carry it out, which, remember, the energy of those photons will then correspond to their frequency and wavelength. And so by looking at the wavelength or color of your light, you can figure out what that energy gap is. Okay, so that tells us something about, that energy gap. All right, so let's start looking at some reactions involving these systems. Now, in general, when it comes to alkenes, you saw that we have a lot of addition reactions across double bonds, right? So, for example, we could do an addition of a hydrohalide across our double bond, and notice that we follow Markovnikov's rule here, right? So our alkene basically does a proton transfer, picks up the proton from our HBr here, and our bromide ion that's left over then attacks the resulting carbocation to form the corresponding, alkyl halide. Okay, and it follows Markovnikov's rule because this carbocation is more stable than the alternative. Okay, now in the case of a conjugated diene, you have 2 alkenes that that are involved here, right? So what gets attacked And, how, right? We get two products that we observe. How do those two products arise? Okay. Now, this example we've got over here is very symmetrical. So why do we see two products in the first place, right? Why don't we just see this one more stable product with, with another double bond, right? So essentially, this product. Where do we get this other product from? Okay. And so to understand that, we're going to look at that carbocation that forms accordingly. Okay, so let's start off with that proton transfer. So our one of our two carbon double bonds picks up that proton and forms a corresponding carbocation. Okay, now again, we've seen that it's probably better to form that carbocation here than here for two reasons. One, this is a secondary site as opposed to a primary site. But more importantly, notice that we have a double bond that's just one bond away, right? This is an allelic system. And so that carbocation is resonance stabilized, all right? So it turns out that both resonance structures of our carbocation, of our allelic carbocation, yield our two products. So this carbocation over here yields that product we were expecting. But notice that if we shift this double bond over, we move that positive charge over here, that yields our other product that we see. Okay, now if you're saying to yourself, wait a minute, isn't that a primary site? Isn't that less stable? Again, don't forget that that resonance stabilizes that. That primary carbocation there is not the same as if we had a primary carbocation over here. Okay, all right. So that's where we get our two products from. Now to distinguish between them, the quick terminology here is an adduct. All right, we call the two processes a 1,2 addition versus a 1,4 addition. And so as a result, you get a corresponding 1,2 adduct or a 1,4 adduct. If you're wondering what the word adduct means, it's a portmanteau of addition product, right? It's just that word contracted. So where does the 1 and 2 come from, right? So if we look at that original alkene, that original double bond, that's carbon 1 and 2 of that double bond, right? So the hydrogen goes to carbon 1 over here. The bromine goes to carbon 2. Okay, so there's carbon 1, there's carbon 2, there's your hydrogen, there's your bromine. Now, in the case of the resonance, okay, the resonance structure, now that carbocation is on the number 4 carbon. So if we look at where the hydrogen and the bromine are, hydrogen's still on that number 1 carbon, okay, but 2, 3, 4, our bromine's on the number 4 carbon, okay, and that's why this is called a 1,4 adduct. Okay. So, of course, this applies to other types of electrophilic addition reactions, okay, not just a hydrohalogenation. So let's say we do a bromine addition, all right. Now, instead of going through just a carbocation, here we actually go through a bromonium intermediate, right? But again, the same principle applies, right? We have, that molecule, that carbocation can be resonance stabilized. And as a result, we still get a 1,2 versus a 1,4 adduct through a very similar mechanism. Okay, so with that in mind, let's try a practice problem out. Go ahead and sketch out the products for this. So ask us to try drawing out the 1,2 and the 1,4 adducts respectively. Okay, notice we have that conjugated pi system. When you look at your products, pay close attention to both the resulting products. You'll see what I'm talking about when we look at the answers. Okay, so if you've drawn those your 1,2 and 1,4 adduct, you'll probably realize that if you don't pay attention to stereochemistry, they're the same molecule, right? While this molecule seems very asymmetrical, when you draw your 1,2 and 1,4 adduct, you'll notice that you're going to have a chlorine basically coming off this point here. Now that being said, you do have some variance here because that is a chiral center. Your carbocation is flat. right? So the chlorine can add to either side, and since you've got a chiral center that forms, you can make the resulting enantiomer as well. You'll get a racemic mixture of both enantiomers. Okay, so that's why this has been drawn, with that stereochemistry shown. Okay, but if you drew another molecule, thinking like, oh, let me draw that 1,4 adduct, flip the molecule over and you'll realize it's the same molecule. Okay, now how do we control the production of these adducts? Well, it turns out that this is temperature dependent, right? So at low temperatures, we tend to get the 1,2 adduct. At high temperatures, we tend to get the 1,4 adduct. Okay, now to understand why, let's have a look at a reaction potential diagram. Look at the energy involved. Okay, so if we we're going through that first proton transfer, of course, is identical for both products, right? We still form the same, we still do that proton transfer, we form that initial carbocation, right? In the case of the 1,2 adduct, right, you do a nucleophilic attack with your, on that number 2 site. Okay, in the case of the 1,4 adduct, of course, we have that resonance structure. And so you've got to ask yourself, how is the nucleophilic attack on that resonance structure different from our original carbocation? Okay, so notice that here that the transition state is higher in energy. So we have a higher activation energy for the 1,4 adduct. But notice that also we have a lower potential energy for the resulting product. Okay, so you want to think about the difference between kinetic versus thermodynamic product here. So ask yourself, is our 1,2 adduct the kinetic or the thermodynamic product? And what about the 1,4 adduct? Okay, so notice that we have a lower transition state, lower energy transition state for the 1,2 adduct. So that's our kinetic product. Whereas the 1,4 adduct has a lower potential energy, so it's more stable thermodynamically. That's the thermodynamic product. Okay, so again, it makes sense going back here. Remember, at low temperatures, your kinetic product is the one that's more likely to form, right? Because you have fewer molecules that meet the necessary high energy barrier to make that thermodynamic product. And that's why there's a lower yield of that. But at higher temperatures, more molecules are able to make that more stable product. Okay. All right. So let's understand why there's the difference. Why is the 1,2 adduct the kinetic product, and why is the 1,4 adduct the thermodynamic product? Let's have a look at that transition state for each of our carbocations. Okay, so over here, notice that we have a more substituted carbocation, right? So that's going to be a little bit more stable, and that's why it's a little bit lower in energy. Of course, if you're trying to understand why is your thermodynamic product at a lower potential energy, you want to look at your alkene itself. Notice that here our double bond is di-substituted, whereas here it's just mono-substituted. And again, that's why our 1,4 adduct is the lower energy, the more stable thermodynamic product. Okay, now while you could just memorize, the 1,2 adduct is going to be our kinetic product, and our 1,4 adduct is going to be our thermodynamic product, I highly recommend you don't do that. And I've kind of pointed this out last semester as well. Like memorizing rules are great. They'll save you some time on quizzes and exams. But you're more likely to make a mistake, especially when you have unusual circumstances. Let me give you an example here. So in this problem, we have a conjugated pi system, as you can see, and we have that typical setup. We have HBr. We're going to do it, your addition reaction of HBr across one of those alkenes. And again, notice we're doing this at a higher temperature and a lower temperature. So we're going to have our 1,2 adduct and our 1,4 adduct, and one's going to be a kinetic product at that lower temperature, and one's going to be a thermodynamic product at that high temperature. Now, you might be tempted to just automatically then say, like, oh yeah, our 1,2 adduct is going to go here, our 1,4 adduct is going to go over here, right? No problem. But that actually isn't the case. The 1,2 adduct winds up being the thermodynamic product at a higher temperature, and the 1,4 adduct winds up being the kinetic product at a lower temperature. So why is that? So if you're having trouble seeing this, again, I recommend drawing out your carbocations and using that to determine what your kinetic and thermodynamic product is going to be. Okay, so if you're having trouble seeing that, go ahead and take a second, draw that out now, and have a look. Okay, so hopefully you should have drawn something that looks like this. So if we start off, we have our proton, transferred over to this number 1 carbon over here. So our initial carbocation is going to look something like this, right? Oops, that's an ethyl group. So here's our alkene. We have a hydrogen that's attached here, so this turns into our carbocation, right? Now, of course, notice our allelic system over here, so we can swing these electrons over here, and that causes this resonance structure that looks like this. So here's the double bond, and instead our carbocations over here on this carbon. Now, notice that notice the difference between these two. Okay, so first of all, having this carbocation yields this product over here, this carbocation yields this product over here, right? Once you have your bromide ion attack. But what's the difference between these two? Well, the really standout difference we see, of course, is that this is secondary carbocation and this is a tertiary carbocation. Okay, so notice that a tertiary carbocation is more stable, and therefore it's lower in energy, and that's why this winds up being your kinetic product. Likewise, this is higher in energy, and this is your thermodynamic product. Also notice that you want to confirm that one product is not both your kinetic and thermodynamic product, and you can see that by just looking at the substitutions on the alkene. Notice that this is tri-substituted, okay, and this is di-substituted. Okay, so that's why this is your thermodynamic product, and that's why you get that at higher temperatures. Okay, of course, if you had one product that was both kinetic and thermodynamic, you would see it as your sole product for both temperature conditions. Okay, but that's not the case here. All right, so again, notice that we've kind of subverted expectations here, right? We would have expected that 1,2 adduct to go over here and vice versa. So that's why I recommend drawing out that carbocation intermediate and using that to determine your answer. Okay, so when it comes to polymerization, we looked at that back in the chapter, back last semester in the chapter on radical reactions. But when it comes to polymerization, a lot of those polymerization reactions rely on a 1,4 addition. Okay, so for example, here we have we take an isoprene monomer and we can form this polymer here. Notice that it's a 1,4 polymer. Okay, that's what causes that polymer strand to grow out as that kind of straight chain there. Okay, so if you want to see the mechanism for that, again, you can go through various intermediates, but let's say we're going through a carbocation intermediate as opposed to an anion or a radical, just so it's kind of similar to the addition reactions we looked at earlier just now. So we have some electrophile coming in and basically turning this into a carbocation. So again, notice that here we have our double bond sort of swinging over. So we're not seeing that resonance structure, but that's effectively what's happening, right? So they've kind of condensed this a little bit. But you can see that our electrophile added on the number 1 carbon, notice that our new monomer is coming in and attacking that number 4 carbon, right? 1, 2, 3, 4. So we're getting that 1,4 adduct, that 1,4 addition that causes that polymer strand to grow. Of course, if we did a 1,2 addition, instead our monomer would attack this carbocation site here, and we'd get a very different looking polymer chain. We'd probably see instead of getting that long straight strand, it would be a little bit more compacted, a little bit more branchy. Okay, so that brings us to pericyclic reactions. So pericyclic reactions, well, we're going to go through the different types, but you're going to notice that they all have one thing in common. They all have a cyclic transition state, okay, hence the name. So let's look at the 3 types involved, starting off with cycloaddition reactions. So in a cycloaddition reaction, we are basically adding a component to our to our diene, to our conjugated pi system, and we're going to make a cyclic compound there. Okay, so essentially, by taking our diene and a dienophile here, we've created a the remaining parts of our ring. Okay. An electrocyclic reaction, basically, you can see here we kind of open up this ring over here, close this ring over here, and a sigmatropic rearrangement, as the name suggests, it's a rearrangement. So it's effectively, you're not really changing the number of bonds, but you are changing their locations. Okay, so notice that this isn't just a simple resonance, right? You're still breaking this bond here. It just so happens you're forming another one over here. Okay, so it's you're breaking a sigma bond essentially and forming a new one. Again, that's where the sigmatropic part of the name comes in. Okay, so let's examine the similarities and differences between these 3 types of reactions. Now, when we're comparing pericyclic reactions, all 3 of them have 4 general features. You're going to have a concerted mechanism. That means there aren't any intermediate. It all happens in one step. All right. Now, that one step involves a ring of electrons moving in a closed loop. All right. Now, that means that the transition state you're going through is going to be cyclic. All right. So I guess 2 and 3 are kind of similar points. And then, generally speaking, the polarity of solvent has no effect on the reaction rate. So what does that tell us? Remember, when do we use a polar solvent? Right? So think back to substitution reactions. Right? Why did we want to use a polar solvent for an SN1 mechanism? Okay, remember that an SN1 mechanism goes through a carbocation intermediate, right? And so having a polar solvent, you'd stabilize that carbocation. So the fact that a polar solvent doesn't have any effect here tells you that there aren't any charged intermediates. You're not using any carbocation or carbanion. So your one intermediate, since you're not dealing with any intermediates here, it's just through one transition state. That transition state doesn't involve any cations or anions, or is generally not charged. Okay. So that being said, let's look at the differences between the 3 types of reactions. To understand this, it might be helpful to look at what bonds are changing. I mentioned that a sigmatropic rearrangement is just that, a rearrangement. You're not really, changing the total number of bonds. Okay, even though you are technically breaking a sigma bond and reforming it elsewhere in the molecule. In the case of cycloaddition and electrocyclic reactions, there are changes in the number of bonds. If we go back to a cycloaddition, notice that we are forming 2 sigma bonds over here. Okay, and notice that out of our 2 reactants, we have started off with 3 pi bonds. Our product has only 1 pi bond. Okay, so essentially we are losing 2 pi bonds, but we're adding 2 sigma bonds. Okay, now look at our electrocyclic reaction here. Notice that we've gone from 3 pi bonds to 2 pi bonds, and we've added a sigma bond over here. Okay, so we've lost a pi bond, but we've gained a sigma bond. Okay, so that's the difference there. Okay, so a cycloaddition involves a change of 2 sigma bonds and change of 2 pi bonds, whereas an electrocyclic reaction involves a change of 1 of each. Okay, so let's start looking at examples of these. The most common cycloaddition reaction you're going to see is going to be the Diels-Alder reaction, also known as a 4+2 cycloaddition. All right, so in the Diels-Alder reaction, you have a diene. Okay, that's the 4 in your 4+2, right? You've got 4 carbons here, okay, in that conjugated pi system. And we have our what's called a dienophile. Okay, so it's a molecule that, well, gets involved in this. And that has 2 sp2 hybridized carbons here. That's the 2 in the 4+2 there. Okay, so those 4 carbons and those 2 carbons form the 6-membered ring of our product. All right, and that's why it's a 4+2 cycloaddition. All right, but that's basically the Diels-Alder. You have a diene with the 4 carbons and a dienophile with 2 carbons, at least 2 carbons, and they combine to form this 6-membered ring. Now, notice that we form sigma bonds, linking our dienophile to the terminal carbons of our diene. And notice that we only have a double bond now between the middle 2 carbons of what used to be our diene. Okay, so again, notice that this is our concerted mechanism. Notice that we have that cyclic transition state where we have our electrons being pushed around in a ring in a cyclic pattern. Incidentally, it doesn't matter which way you draw these 3 arrows. You could have drawn them going the opposite direction. Doesn't really matter. But that's how we make that product. Okay, so yeah, so that's basically what that looks like. So if you want to see what the transition state looks like, it kind of looks like this. So we draw it flat over here, but in 3 dimensions, it probably looks something a little bit more like this. If you're trying to figure out why that is, remember, you've got unhybridized p orbitals here sticking out, and likewise you've got them here. You're forming sigma bonds where you have a direct overlap of those orbitals, right? We're not going to, form a pi bond where we have a lateral overlap. So with that direct overlap, it helps to sort of stack one on top of the other. Okay. By the way, the orientation of this group over here can yield our endo or exo product. So here we have an exo product because that group is, the substituent sticking outwards. We could have had it tucked underneath and sticking inwards to make the endo product. All right. Here's the energy diagram for that reaction. So notice, of course, our transition state is at the highest energy there. Notice we have only one big hump for this. There's no intermediates. It's one concerted step. And notice that we have our product here at a lower potential energy. Okay, which makes sense, right? We've broken these low energy pi bonds, and we've formed these more stable sigma bonds. Okay. Yeah. So when I say low energy, it costs little energy to break them. That means that they were at a higher potential energy to begin with. Okay, so that's why they're up here. Sorry, I realize that statement could be confusing. It depends on perspective, right? So it's low energy in terms of the cost to break these, but that's because they're at a higher starting potential energy. The sigma bonds are stronger, but that's because they're at a lower potential energy. It costs more energy. It would cost more energy to break those carbon-carbon single bonds. Okay, now, in addition to a Diels-Alder reaction, you could do the reverse reaction, what's called a retro-Diels-Alder. Typically, high temperatures favor your retro Diels-Alder, which can be kind of tricky when you're trying to do a Diels-Alder reaction, because that means that since you're doing this at a lower temperature, you also have a lower rate of reaction, right? So if you're trying to increase the rate of reaction, you've got to be careful about trying to do that thermally, right? Because the higher temperature will, instead of giving you more product faster, it winds up giving you less product, more if your product breaks apart to go back to forming your reactants. Okay. If you want to try and understand the thermodynamics of this reaction, all right, since we've already looked at the enthalpy, right? We've seen that our product is at a lower potential energy, right? So this is an exothermic reaction, generally speaking. Think about the entropy of this reaction as well, right? We have two reactants forming one product. So ask yourself, is delta S going to be a positive or negative number? Okay. Well, so since your entropy is going to be decreasing, you're going from more reactants, more free-moving molecules into one product, you're decreasing entropy there. So delta S is going to be a negative number, which means negative T delta S, that term, is going to be a positive term. Okay, so if we look at our Gibbs free energy equation, delta G is equal to delta H minus T delta S, this entropy term is going to be a positive term. Okay. At the same time, we saw that the enthalpy is going to be negative, right? This is an exothermic reaction because we're breaking, we're effectively converting 2 pi bonds into 2 sigma bonds. That releases energy. Okay, so this term is negative, this term is positive. So if we want this reaction to be spontaneous, we need delta G to be negative. So we need this term to be bigger, and we need to make this term smaller. So how do we make this term smaller? We make the temperature lower. Okay, and that is why basically our low temperatures favor the Diels-Alder reaction. Okay, but as I pointed out earlier, there's that drawback of, from a kinetic standpoint, if you lower the temperature, you're also slowing down the rate of the reaction. So yes, you'll make more Diels-Alder product, but it takes longer to form it. Okay, so now I mentioned the terms diene and dienophile. So when you're looking at your Diels-Alder reaction, you want to be ready to identify those. Okay, so just I'm using those terms there just so you're aware. So notice that your dienophile in this case has a double bond in it. Okay, so it's, in this example here, it's an alkene itself, but it's called a dienophile because it's attracted to and reacts with our diene. Okay. All right. Quick note here about our dienophile. Notice that we've drawn a substituent on it. That substituent makes a difference. Okay. Typically, when you do not have a substituent on here, this reaction is generally not very favored. You need a high temperature to try and force it, but as we've seen, high temperatures aren't good for that forward reaction. So you're going to get a very low yield, right? So what can we do to encourage this Diels-Alder reaction to take place? What substituent can we have here? What can we have here as X to encourage this reaction? Okay, well, as I've kind of given away here, it helps to have an electron withdrawing group of some sort. Okay, so we typically have some sort of electron withdrawing group. We've got lots of options here, and that kind of sucks electron density away from that alkene. So even though alkenes are normally relatively electron rich, this one's going to be relatively electron poor, and that's what encourages that diene to kind of push electrons towards it. Okay, so yeah, if you're having trouble seeing how these groups are electron withdrawing, try drawing resonance structures for these. So all of these can have, you have a conjugated pi system with that carbonyl over there. You can't see it here with the nitrile here, but there's the triple bond between that carbon and that nitrogen. So likewise with your carbonyl, you can have resonance structures where that electronegative oxygen or nitrogen can get the can get an extra lone pair by having the electron swing upwards towards it. So if you're having trouble seeing that, let me illustrate it here with one example. So basically You can have electrons swing up here and electrons swing up here, and you put a negative formal charge here. Have an extra lone pair on that oxygen. But that's again what makes this rather electron poor. Okay, and that's what makes this group electron withdrawing. All right. So regarding your when you're looking at the stereochemistry of your dienophile, that will determine the stereochemistry of your product as a result. So here, notice that our dienophile is an alkene, and notice that here we have a cis alkene versus a trans alkene, right? Or you could use E or Z notation, right? Remember, if you're having trouble distinguishing them, Z or Zusammen, the quick way to remember it is the both groups here on Z same side of the double bond. So this is your Z alkene, all right. But notice that in this case, this cis alkene has both of these substituents, cis in the product. Okay, whereas here we have a trans alkene, and notice that those substituents are trans in the product accordingly. Okay. All right. Now, while all the examples we've looked at so far happen to have been alkenes, the important thing is you have a pi bond there, right? So it doesn't matter if you have more than one. It's possible to use an alkyne as your dienophile. Okay, so notice that when we do that, notice that we still have a leftover pi bond. So instead of forming just a sigma bond here, or having just a single bond here, we wind up having a double bond. Okay, so let's practice this. Have a look at these, these two reactions, and try and predict the products. In the case of the second one, they've actually given you the product. They're asking you what reactants would have made that Diels-Alder product. So in other words, think of it as a retro Diels-Alder, and ask yourself what this breaks up into. What's the resulting diene and dienophile going to look like? Okay, so hopefully if you've paused this and come back now, we can have a look at these answers, and here you go. So don't forget to consider stereochemistry here. So notice that, so here's your alkene, and based on how you have your, this carbon is symmetrical, right? We have two methyl groups, but this one is not, right? We have a hydrogen and we have our electron withdrawing group. So depending on whether that group is pointing towards or away from us, it's going to cause that group to be, well, represented with either a dash or a solid wedge. Okay, and of course, based on which way this sort of stacks on top of the other, that methyl group is going to be pushed to the opposite side, right? So if this one's pointing away from us, this methyl group is pushed towards us, and vice versa. For this molecule here, the fact that you have a double bond over here tells you, a double bond here and a double bond here, tells you that your dienophile was probably an alkyne. Okay, now if you're having trouble when you look at this and you're trying to figure out, well, what side, which end of these was the diene and which one was dienophile, look for the electron withdrawing group, right? You see this nitrile group over here, and you know that that's an electron withdrawing group, so it tells you that this was probably the side with your dienophile, which means that these four carbons here were your diene. Okay, and so your double bonds were here and here originally, and that's kind of what that looks like here. Okay, so we formed a bond between this carbon and this carbon, and we formed another bond between this carbon and this carbon, and we shifted around those pi bonds accordingly. Okay, now earlier in this chapter I talked about S-cis and S-trans rotational conformations, right? Now, while S-trans conformations are more stable, we need the S-cis conformation for Diels-Alder reactions. Okay, with the S-trans conformation, those two carbons are too far apart to form our link with our dienophile. Okay, so you do need that S-cis conformation, to form that 6-member transition state and therefore go on to the product. The fact that you go through a 6-member transition state also tells you why you need that cis conformation as opposed to trans, right? You can't have a ring of fewer than 8 carbons with a trans bond in them. So something to keep in mind. Okay, so yeah, so again, here's that illustration of that. So here you can see that we have an S trans conformation and it's locked into place because of this ring over here. This diene is not capable of doing a Diels-Alder reaction. Okay. Yeah. Oh, by the way, when you have molecules that are kind of locked into S-cis conformation, like cyclopentadiene, for example, they readily go through Diels-Alder. So much so that cyclopentadiene actually winds up reacting with itself. One molecule will act as a dienophile to the diene. So if you're having trouble seeing that, here, let's draw an example so you can see what I'm talking about. So here's cyclopentadiene. Okay, so there's cyclopentadiene, and here's another molecule of cyclopentadiene. Okay, the alkene over here, the double bond over here, is going to be our dienophile. Okay, so this carbon is going to link together with this carbon is going to link with this carbon, and that's how cyclopentadiene can act as its own dienophile, right? So you wind up actually forming a bond here and here, while this shifts around. So like that forms here, and that goes there. Okay, and so you wind up forming that. So you wind up actually getting a bicyclic product. This carbon over here winds up sticking out. So there's your 6-membered ring between those. This is what used to be your dienophile. So that still continues here, with this double bond still here, and there is a link between those two. There we go. All right, so that's actually what your product looks like when you have cyclopentadiene reacting with itself. All right, so here's cyclopentadiene, here's a dienophile. Go ahead and draw the 4 potential products for this. Okay, now keep in mind 2 of those are going to be impossible. Well, we'll figure it out when you try drawing them. Okay, so here are the 4 possible products. Please note that the trans products listed here are impossible because your dienophile, notice that the substituents on that are cis. Okay, so really, even though we've drawn down, 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 up, up, and up, down, those are the 4 combinations that you can possibly get. Please keep in mind that these 2, down, up, or up, down, are both impossible, just because they don't line up with the alkene, with the dienophile that we used. Okay, so that being said, when we look at these 2 possible products, how do we get these 2 possible products? Well, again, it depends on how you stack your diene and dienophile. Does your does this sort of sit on top of this, or do you have these? Does this sit on top of this with these substituents pointing outwards, or are they tucked underneath? When they're tucked underneath, this is where we get that endo product, as opposed to the exo product where they're pointing outwards here. Okay, so let's talk a little bit more about that. Okay, I've used those terms endo and exo before. Exo means outwards, endo means inwards. What do we mean in terms of the in terms of a molecule like this, our cyclic compound? So in this case, with cyclopentadiene, we're going to form a bridged compound, right? Where since you're starting off with a ring in your diene, that carbon that's part of that ring will form a bridge of its own. Okay. The main part of what used to be your cyclopentadiene, though, it's basically going to be syn in with your endo product, or it will be anti with your exo product. Okay. Now, notice that with your exo product, if it's anti to that larger bridge, that's a good thing from a steric standpoint, right? The bulkiness of this and the bulkiness of whatever is over here, they're not clashing as much as if you have them in that endo position, right? There's some steric hindrance in between these two groups otherwise. So while you would think that then, your sterics would determine the product and you'd expect that the sterically more stable exo product should be the major product, that's actually not the case. We wind up seeing that the endo product is our major product, whereas our exo product is the minor product, okay, even though it's more sterically stable. Okay, so why is that? Well, if it's not sterics, then that tells us there's an electronic reason for this. Okay, so remember that we've got these are electron withdrawing groups over here. Okay, the reason for this then, from an electronic standpoint, has to do with the sort of interaction, that sort of overlap we have between our pi system and our and those electron withdrawing groups. That attraction causes the diene and your dienophile to sort of stack with those electron withdrawing groups closer to your pi system. Okay, so again, this is an electronics argument in favor of that major product for why we get that endo product as our major product. Since we're arguing from the standpoint of the stability of this transition state, please note that this is a kinetic argument. Okay, with a thermodynamic argument, we'd be arguing for the stability of the final product, which I've already pointed out is not the case. This endo product should be less stable due to steric hindrance. Okay, so here is a sort of just a little sketch of what the diagram looks like. So again, for your endo product, this transition state is going to be at a lower energy, even if this product is at a higher potential energy, right? So if we were to draw this for your exo product, the transition state would be higher up, though the product would be at a lower potential energy. Okay, so when it comes to cycloaddition reactions, again, understanding our molecular orbitals and the way they are lined up will go a long ways to help you understand what's going on and predicting the products, the stereochemistry of the products that we expect to see. All right. So in the case of our, Diels-Alder reaction, right? Here we have our butadiene, which is our diene, obviously. And here we have ethylene, or ethane, as our dienophile. So let's look at the frontier orbitals for that. So here we can see that, of course, out of our four molecular orbitals for our butadiene, two of them are occupied, two of them are unoccupied, and here are the those frontier orbitals. And for our ethene, out of our two molecular orbitals, this one with complete overlap here is our occupied one, whereas the antibonding, the pi antibonding orbital is our LUMO, right? It's unoccupied. Okay, when we have our Diels-Alder reaction, the LUMO of one of our compounds must interact with the LUMO of the other. Those electrons in the HOMO get donated into the LUMO of the other molecule. Okay, so we can see that here. So again, ignore the unoccupied orbitals on our butadiene. Look at the occupied ones. These electrons get donated into the LUMO here. In doing so, that's where we start to break that that pi bond between the two carbons in our dienophile, which makes sense. We're going to be breaking that pi bond anyway, and it's going to go towards forming one of the sigma bonds that we see between our diene and dienophile. Okay, so you can see here that so we have that opened up, and we have interaction now between those p orbitals on our diene and our dienophile. Now, up until now, we haven't really paid attention to the phase of those p orbitals, but this is actually really important for the way the reaction happens. All right. Um, it's essentially in order for the reaction to occur as we see it, we need to have what's called a symmetry allowed process. Essentially, the phases of our orbitals have to line up. So you can see here, for example, the red lobe on this p orbital lines up with the red lobe on this p orbital, and over here it's blue and blue. Note that this lines up with the HOMO of our diene and our LUMO of our dienophile. Okay, so if we go back, to this diagram, notice the phases of those p orbitals, right? So if we look at the HOMO of our butadiene, notice that the outside two carbons have opposite phases. Okay, likewise with our what is now with our LUMO on our ethylene, notice that those also have opposite phases that allow them to line up with those outside carbons. Okay, so that's what we kind of observe there. So if these were not lined up, so for example, let's say these two lobes were the same color, or maybe these two lobes, we wouldn't be able to have that overlap, and we wouldn't be able to form the sigma bonds that we need to form over here. Okay, and so that's why it's very important that these orbitals line up, that we have this symmetry allowed process. Okay. Let's have a look at a 2 plus 2 cycloaddition. So here we have two ethylene molecules, two ethylene molecules, and we're going to try and make cyclobutane out of it. Okay, now if you were to draw a mechanism for this, it seems like it would be pretty similar, right? You would just have, our pi electrons swing up from this double bond and swing down from this double bond, or go in the opposite direction, and that's where these sigma bonds would form, making this ring, right? But you'll see that when we try to look at the molecular orbitals for this doesn't make as much sense. Okay, so here's that conserved mechanism I talked about, and like that seems logical, right? That seems like, okay, we push these arrows around, that works. That's where these bonds come from. But does this make sense from a molecular orbital standpoint? Let's draw out the HOMO and LUMO for our two molecules. And so they're both the same molecule. So the two molecular orbitals we're going to look at are going to be the same for each of them. Your HOMO is, of course, the one where both of your p orbitals are lined up. Okay, so you have perfect overlap. The LUMO is going to be this one where they're not lined up, and therefore you have a node between the two. Okay, so remember, the HOMO of one of your ethylene molecules is going to donate into the LUMO of the other ethylene molecule. Okay, now notice the symmetry on both of these frontier orbitals. Okay, so if you have this HOMO on this ethene molecule and this LUMO on the other ethene molecule, while we do have an overlap between these two red lobes, notice that we cannot have an overlap here. So even though we could draw an arrow pushing mechanism that could explain the formation of the product, we can see that this product will not actually form. Okay, we say that this reaction is symmetry forbidden. Right? It's not symmetry allowed, it's symmetry forbidden because the orbitals don't line up to allow it. Okay, so how can we do a 2 plus 2 cycloaddition if it's possible to push those electrons around? Well, this involves changing what is your HOMO and what's your LUMO. So to do this, you can actually excite an electron up using light. We've seen that before. So in its excited state, now your HOMO is no longer this molecular orbital where you have this perfect overlap, but instead the excited state has its HOMO as the one where you've got both of your orbitals out of phase. Well, that the HOMO on one molecule that is excited will line up with the LUMO of an unexcited molecule, okay, of a ground state molecule, and then now we have a symmetry allowed overlap. Okay, as long as one molecule is excited and one's in the ground state. All right, so let's have a look at some electrocyclic reactions and look at that mechanism, and we'll also see basically how molecular orbitals play into these as well in a little bit. All right, so in the case of electrocyclic reactions, we've seen that we essentially swap out a pi bond for a sigma bond, right? So here you can see that we go from having 3 pi bonds, we go down to 2, and notice that we've formed an extra sigma bond over here. Likewise, here we've got 2 pi bonds that have dropped down to just 1, and likewise we've formed an extra sigma bond. However, look at the equilibrium, the ratio between our products here. For this one, we are product favored. Over here, we're reactant favored. Right? Notice that this arrow, the reverse reaction, is favored over the forward reaction. Okay, so think about why that might be. So that comes about, of course, from the ring strain of having a 4-membered ring here, including a double bond, right? That bond angle is being, it wants to be 120 degrees for that sp2 hybridized carbon, but it's cramped into 90 degrees, right? Whereas the 6-membered ring is a little bit more stable. All right, now when you have substituents on your terminal carbons, it's possible to get isomers, right? We could have our substituents be either cis or trans to each other. Now, how that happens depends on how our ring opens and closes in the process of this electrocyclic reaction. All right, so you can see that if those carbons turn one way, we can have these methyl groups either pointing outwards or in this case inwards, and accordingly when the ring closes, they can be pointing up or down. Okay, in this case they're both pointing in the same direction. Here they're pointing in opposite directions. Okay, now how do we vary what happens? Well, if you look at these arrows, you can see that our reactions are different depending on whether we use heat or light as our energy source to encourage the reaction to take place. All right, so we're going to see what happens there in a second. Okay, so again, the symmetry of our orbitals are going to determine the products that we form, right? It determines how those carbons are going to turn in order to have a symmetry allowed outcome. Okay, so if you want to figure this out, the best way to go about this, of course, is draw a quick molecular orbital diagram by sketching out those p orbitals. Again, you don't need to draw the actual molecule or anything like that. Like just lining up 4 p orbitals like this would be sufficient to do that, right? And to see what kind of symmetry are we dealing with. Okay, so what this comes down to is how do the p orbitals on those outermost carbons, the ones that are going to form your the sigma bond that closes the ring, what way do they turn so that their orbitals overlap properly, right? They have the same phase overlapping. Well, if they are lined up in the same phase like this, okay, as you can see, they're kind of like, both have blue on top, red on the bottom, or if they were vice versa, we have what's called a disrotatory rotation. Okay, basically one of them turns clockwise and one of them turns counterclockwise or anti-clockwise, and in doing so, the red lobes overlap. Now, we could have done this the other way. We could have had this one turn clockwise, this one turn counterclockwise, and the blue lobes would overlap. But in both cases, one's turning clockwise, the other's turning counterclockwise. That's why this is disrotatory. Okay, I think what confuses a lot of students when they see this happening, this looks very symmetrical. But the prefix dis there makes people think not symmetrical, which is not the case. It's one's going clockwise, one's going counterclockwise. That's the dis part of the disrotatory. Okay, now while these carbons with their orbitals are rotating, what's happening to those to the methyl groups that are attached to those carbons? Well, if this is turning counterclockwise, this methyl group is swinging downwards. If this is turning clockwise, this methyl group is also swinging downwards. And they wind up being cis to each other. Okay. So now this is not always the case. It kind of depends where our methyl group's pointing in the first place. All right. But in this case, they were both pointing sort of outwards, and by rotating downwards, they wind up being cis in the final ring closed product. Okay. So here you can kind of see the effects of different starting positions on those methyl groups for what we observe. So, for example, here, so in both cases we have a disrotatory rotation, right? And so if this one moves, um, oh, sorry, not disrotated. This is going to be conrotatory, as we're going to see in a second. But we can see here that this methyl group winds up pointing away from us. So if we were looking at this carbon, um, it's kind of turning clockwise. Likewise, this uh, methyl group is going to be pointing towards us. Okay, so this carbon's turning clockwise as well. Okay, that's a conrotatory rotation. Okay, con means with, dis means against. So it's a conrotatory rotation. Now, look at the orientation on these two methyl groups. This methyl group is pointing downwards as opposed to this one that's pointing upwards. Okay? So, in order for it to wind up pointing towards us here, instead of, it still wants to rotate clockwise, right? It's going to start moving from here upwards towards us. It's kind of hard to explain this verbally and not do this with a 3D model. But if you have one in front of you, I recommend trying to rotate it so you can see this. Okay, but basically, this methyl group is going to start pointing towards you if you start rotating. If this were a single bond and you started rotating this clockwise. Okay. Likewise, if you want this methyl group to point upwards, you'd also rotate this clockwise, and that's why this is also a conrotatory rotation. Okay. So notice how the difference in starting point for that methyl group gives you a trans versus a cis product when you do a conrotatory rotation. Before I move on, let me just quickly show you why this particular molecule has a conrotatory rotation instead of a disrotatory rotation. Again, if you want to know which one it's going to be, it helps to sketch out the molecular orbitals and see which way those orbitals need to rotate in order to overlap properly. So for this particular molecule, or for either of these, we have four carbons that are involved in this conjugated pi system, right? There's two double bonds here, so two pi bonds. So that's four pi electrons that are involved. So if we were drawing out our molecular orbitals for this, right, we'd have four carbons that are involved, and we'd have four molecular orbitals. Now, we're doing this with heat, so really our HOMO here is just going to be the second out of the four orbitals. So I'm not going to bother drawing the third and the fourth just because they're unoccupied and they're not really important. We're interested in that the HOMO over here, all right, that highest occupied molecular orbital. So the lowest energy one overall, of course, will have no nodes where everything's in the same phase, whereas this one, this highest occupied molecular orbital, is going to have one node where these two, these two orbitals are in the same phase, these two orbitals are in the same phase, but if we look at the outside two carbons, they're in opposite phases. So that's this carbon here and this carbon here. So that's why you need to have a conrotatory rotation. Unlike the previous example where you had both the same color lobes on top, so the disrotatory rotation caused them to overlap. Here, they're on opposite sides, so they need to do a conrotatory rotation. So in other words, it would look kind of like this. Here are those two outside orbitals. They're kind of connected, via this string of carbons, right? But if this one is oriented this way and this one's oriented this way, this is going to rotate clockwise, and this also rotates clockwise, so that we have an overlap accordingly. If you need a visual for the conrotatory or disrotatory rotation, which I obviously can't show you on a PowerPoint, I actually normally use my hands to illustrate the way the orbitals rotate, or the carbons rotate to get their orbitals to overlap. So I use my thumb and pinky as sort of the different phases of a p orbital. So, for example, if both your p orbitals are lined up the same way, like let's say my thumbs are the red lobes and my pinkies are the blue lobes, and they're both oriented in that same way, notice that in order to get that overlap between my thumbs, therefore the same types of lobes, we do this sort of disrotatory rotation. I rotate one way with one hand and the other way with the other hand. So from my perspective, at least, this hand's going clockwise and this hand's going counterclockwise. So that's how that overlaps. If you want to see a conrotatory rotation, imagine that now we have my thumbs on opposite sides here, right? So if, in order for that to happen, notice I turn my hands the same way. That's a conrotatory rotation. And to do that, there my thumbs overlap that way. Okay, so if you're ever having trouble visualizing this or building a model to represent that, using your hands is not a bad way to go about it. Now, what about the methyl groups that are attached to those carbons that are rotating? So again, I'm going to use my thumb and pinkies as the p orbitals. I'm going to extend a finger. I'll use my index finger to avoid making too rude a gesture at you guys, to represent a methyl group that's sticking out. So let's say I have both of my p orbitals that are, are aligned in the same way, all right? And let's say both of my methyl groups are pointed inwards, okay? So now, in the case of my p orbitals being in this orientation, they're going to do that disrotatory rotation to overlap, right? So now my methyl groups, which are pointing to the middle, would then wind up being cis. They're both pointing downwards when I do that. Likewise, if I wanted to get my pinkies to overlap, both those methyl groups are now pointing upwards. Again, they're still cis. All right. What happens if my one of my p orbitals is oriented the other way? All right. So if one of them's upside down, so I want to again do a conrotatory rotation and get my thumbs to overlap here, and I have both of my methyl groups pointing inwards. Notice that when we do our conrotatory rotation, now these methyl groups are trans to each other. Again, if I were to rotate the other way to get my pinkies to overlap, those methyl groups are still trans to each other. All right. What if we have a methyl group, one methyl group pointing inwards and one methyl group pointing outwards? Now, if our p orbitals are lined up, so we do a disrotatory rotation, now notice that our methyl groups are trans to each other. Okay, and same thing if we were to rotate our pinkies. If we had the same setup, this is going to be a little awkward. There we go. Now our p orbitals are upside down, and I've got one methyl group pointing inwards, one methyl group pointing outwards, and we do a conrotatory rotation. Oops, there we go. Notice that now our methyl groups are cis to each other. All right, so those are basically the 4 different variations you can see of which way your methyl groups are going to be pointing, whether they're going to be cis or trans, depending on whether you have a disrotatory or a conrotatory rotation, and depending on if the methyl groups are both pointing inwards, or one's pointing inwards and one's pointing outwards. I just realized I recorded that whole previous segment referring to the substituents on our carbons as methyl groups. I just want to clarify, obviously it doesn't have to be a methyl group. You could have an ethyl group. And in fact, I think we have an example problem where we have an ethyl group sticking out instead, or 2 ethyl groups sticking out instead of methyl groups. You can use any, there can be any substituent. It doesn't have to be a methyl group. All right, I just refer to a methyl group because that's what happened to be the substituent in the first example we did. So let's let's look at this example here and predict what the product's going to be. Again, when you're trying to predict this product, first of all, here's your six-membered ring, right? That's your conjugated pi system. We're going to be forming a sigma bond here. So my advice is taking these six sp2 hybridized carbons, sketch your molecular orbital diagram. Okay, at least the HOMO for that one, the highest occupied molecular orbital, and look at the hybridization of these two p orbitals, and ask yourself, how are they going to rotate to overlap? And when they do that, is it a conrotatory or disrotatory rotation? And as a result, since these two methyl groups are pointing outwards, will they wind up being cis or trans in the final ring-closed product? Okay, so feel free to pause this video if you'd like to try this, take a stab at this on your own. And if you're back with us now, let's have a look at how that answer works. Okay, so here's what the products look like. Notice that we wind up getting a cis product. Okay, either they're both cis pointing upwards or cis pointing downwards, depending on which way you rotate those carbons, but it's going to be a disrotatory rotation that does that. Okay, so if we rotate this carbon clockwise, this methyl group swings upwards towards us. Likewise, we rotate this one counterclockwise, this one swings upwards towards us, and that's why we have these cis pointing towards us. Okay. Likewise, if we rotated this counterclockwise and rotate this one clockwise, those methyl groups would be cis pointing downwards. Okay. Now, the question, though, you should be asking yourself before we get to this final answer is, how do we know it's conrotatory or disrotatory? Right. So you want to sketch out those orbitals, and in order to figure out what they look like. So we have 6 carbons here. Okay. So we have 1, 2, 3, 4, 5, 6 carbons, right? And there's going to be 6 molecular orbitals, but to be honest with you, you only have to draw 3 of them because the top 3 are going to be unoccupied, right? We want to just look at that HOMO. Okay, so out of these 3 bonding orbitals, the lowest energy one will involve everything being in the same phase, right? So all of these are overlapped, there's no nodes. This next step up will have 1 node, so that means we'll have 3 of these that are in the same phase and 3 of these that are in the same phase, but there's a node here, so these 3 are different from these 3. For this one, there's going to be 2 nodes, so we're going to divide this into 3 sections, which means that this one will have these 2 overlapping like that, these 2 will have the opposite phase to that, and these 2 will be the opposite phase to that, or in other words, the same phase as this one, which tells us that these 2 carbons are in the same phase. And that tells us that this has to swing downwards, this has to swing, as well has to swing like that to get these 2 lobes to kind of meet. Sorry, it's probably a little harder to visualize this on a 2D screen when you want to try and see this in 3D. So again, I recommend drawing this in, trying to build a model here and seeing how this rotates. Okay. Yeah. So basically, it's going to be a disrotatory rotation. So here, the way I've drawn this is a clockwise and this is counterclockwise. That's why it's disrotatory. But that's what gives us this cis product. All right, so that's what happens with heat. However, this outcome gets flipped when we do this under light conditions. So when we would do this in the presence of light, it changes that it changes our molecule from being in the ground state to being into an excited state. So how does that affect our product? Well, it changes what our HOMO looks like. What used to be our LUMO is now the HOMO. So using the previous example, we saw that this was our HOMO in the ground state, right? Where this outside carbon and this outside carbon were in the same phase. But If we shine light on this and we excite this, we go to the next molecular orbital, which was previously unoccupied. It now becomes occupied. One electron gets bumped up into that orbital, and it becomes the new HOMO. Now, in this molecular orbital, there are 3 nodes. And in order for that to work, it looks like this. Notice that our outside carbons have opposite phases. Okay? So now your rotation has to be different to get an overlap. Okay, to get this blue node and this blue node to lobe to interact, you actually have to do a conrotatory rotation. You have to rotate this clockwise and this clockwise, and they overlap that way. Or if you turn them counterclockwise and counterclockwise, the red lobes would overlap. But my point here is that you still have to do a conrotatory rotation. Okay, so here you can actually kind of see that a little bit more easily. So so basically, if we want to get our blue lobes to interact, so this swings clockwise down here, this swings clockwise up here, and we wind up getting an overlap that way. Okay. Alternatively, we could have swung this counterclockwise, where this red one comes up and this red one comes down, and have the red lobes interact. But the bottom line is it's a conrotatory rotation, which means that our methyl groups are going to rotate the same way as well. In this case, though, if this one rotates clockwise, it starts pointing upwards. This one rotates clockwise, it points downwards, and our methyl groups wind up being trans to each other. Okay, so that's actually what we observe. Okay, so it's a conrotatory rotation, and we get a trans product. Okay, again, just as before, though, the fact that this product is trans is related to the fact that these two, it's a combination of that conrotatory rotation and the starting position of those methyl groups. Because those methyl groups were both pointing outwards like this, that's why the conrotatory rotation made a trans product. Okay, if one of these methyl groups was pointing inwards, and you did a conrotatory rotation, you'd get a cis product. Okay, likewise, with this starting reactant where these methyl groups are pointing outwards, if you do a disrotatory rotation, you would also wind up with a cis product, not the trans product as we see here. Okay, so with that in mind, let's try this again. Notice that here we have this molecule being held under light conditions. Please note that even though this looks similar to the molecule we used in an earlier problem, it is not the same molecule. Notice that we have only 2 pi bonds here, so we have only 4 carbons that are in a conjugated pi system. Okay, so again, I recommend sketching out those molecular orbitals with only 4 carbons, so it should be relatively easy to draw there. And keep in mind that since we're doing this under light, what used to be the LUMO in underground conditions, in the ground state, now becomes the HOMO with, once it's in the excited state. Okay, so keep that in mind. So look at that excited state HOMO and ask yourself, all right, how are these carbons going to rotate to overlap and close the ring? And when they rotate, how are these ethyl groups going to be are going to move? Okay, so again, think about, is it a conrotatory or disrotatory rotation, and then are these ethyl groups going to be cis or trans to each other? Okay, so if you've tried this out, you should hopefully have figured out that this is a disrotatory rotation. Okay, and in doing so, since both of these groups are pointing inwards to begin with, that disrotatory rotation makes them cis. Okay, so they'll either both be pointing upwards or both be pointing downwards, depending on which way you rotate these. But the disrotatory rotation is necessary because when you draw the HOMO accordingly, you see that we've got the 2 outside carbons have the same phase, so they have to have a disrotatory rotation to get those lobes to overlap. Okay, if you're having trouble again trying to draw those molecular orbitals, hopefully you're starting to get the hang of it, but it might take a little practice. So just to show you how we figured out this was the HOMO, let me draw out those molecular orbitals. I'm going to go back a slide where I have a little bit more empty space to do that. Okay, so remember, you've got 4 carbons here that are part of this conjugated pi system, right? You have 2 pi bonds, so you know that it's going to involve 4 carbons. So here's our 4 carbons, okay, and you know there's going to be 4 molecular orbitals, okay. So I'm just going to draw. I only really need to draw 3 of them. The fourth one is, where everything, there's 3 nodes, nothing overlaps. That's not going to be involved here. Okay, that's going to stay empty. So we have our lowest energy one. I'll tell you what, I'll draw it just so that it's complete, so you can see it, but we're not going to need it. Okay, so we have our lowest energy one where everything overlaps, right? Okay, and this has 2 out of our 4 electrons. We have this one where there's 1 node, so we've got 2 that overlap here, 2 that overlap here, but we have this node in the middle here, and so that that's our that's why these 2 have to be in opposite phases. And again, this has those remaining 2 electrons out of our 4. So this is the HOMO in the ground state. Okay. Next we have what would normally be our LUMO. So here there's going to be 2 nodes. Okay. So we have an overlap between these 2 middle ones, but the 2 outside ones, are separated with a node, so they've got to be opposite in phase there. And then, of course, as I mentioned, this one, everything's out of phase. But again, that's not really important. We're never going to put electrons up here as far as this mechanism goes. Okay, so again, if this were a ground state, if this was done with heat, we would just pay attention to the phase of this and this. But since we're doing this with light, we're going to move one of these electrons up here, and this now becomes the HOMO that we pay attention to. Okay, this is no longer the LUMO, it's the HOMO, and now we've got to look at these 2 orbitals on these 2 carbons here, and notice again that they are in the same phase, which means, as we see here, they wind up doing a disrotatory rotation to overlap. Okay, so this here we see it rotating counterclockwise. This one rotates clockwise, but that gets the 2 red lobes to overlap. Okay, if this starts swinging counterclockwise, this methyl group starts pointing downwards. If this swings clockwise, this methyl group also points downwards, and that's why we get this product here. Okay. So so basically that was for a ring closing reaction. The same sort of dynamics apply with ring opening. Okay, you just want to think, kind of think backwards from your ring closing. Okay, so once the ring, if you looked at that reverse reaction and the ring opened, what would it yield? Okay, would it yield the LUMO we'd expect, or sorry, the HOMO we'd expect for a ground state if it's under heat conditions, or would it be for the excited state that we expect under light conditions? Okay, so you're kind of doing this backwards. So here you can kind of see that here we've kind of closed this ring here and we've got a double bond over here. So you could imagine that this bond across from it was the one that we formed. So the product we're going to have here is where this is opened up, okay, and we have a double bond here, and this is a single bond. But the question you've got to ask yourself is, are we going to do a conrotatory or disrotatory rotation to do this? Okay, so again, draw the 4 p orbitals on these 4 carbons that are involved, and ask yourself, what would the HOMO look like for, in the excited state, right, light, that would close to give us this product? Okay, so we had that, so basically it's kind of similar to how we drew a 4-carbon molecular orbital system before, right? You have, I think I had this up for the previous example, but let me draw the 3 out of those 4 orbitals, since that highest energy one really isn't that important. So of course we know that the lowest energy one has a complete overlap like this. The next one up has 1 node, so it looks like that. these two are going to be different. And then the next one up from that has two nodes. So these two overlap and these two don't. And of course, if this were under heat conditions and this, and this were in the ground state, this molecular orbital over here would be our HOMO, right? But since this is under light conditions, whoops, violated Pauli exclusion principle there. So instead, we excite one electron up here, and this is our HOMO. So again, notice that we have these in the same phase, which means that we have to have a disrotatory rotation for these two p orbitals to overlap. Okay, and of course, I know the question kind of gives that away here, or it tells us that it's a disrotatory rotation, but if you ever have to figure that out for yourself, this is why. So sort of think of this problem in reverse, right? So here's the answer, but you could just easily imagine that these were your reactants, and you were doing a ring closing to make this product, okay? And that's why it rotates the way it does. Okay, so if this is a disrotatory rotation, which way are these ethyl groups pointing when you open up this ring? Okay, well, if it's disrotatory, while one moves clockwise, the other is going to move counterclockwise. Okay, so if let's say we're moving this carbon counterclockwise, okay, so it's pointing away from us. If we move it counterclockwise, okay, looking at this carbon bond over here, this is going to swing around and point inwards. Okay, so that's kind of what we see over here. Okay, it's pointing inwards, or well, like to the middle of the molecule. Likewise, this is going to move. If this is a disrotatory rotation, this is going to move. So this one moves counterclockwise. So this one's going to move clockwise, and so it's pointing towards us. It's going to start pointing outwards. I guess I've kind of drawn this. It's kind of hard to see this again in 3D when looking at a two-dimensional screen, but so imagine that this is going from pointing towards you. I guess it's kind of think of it pointing downwards like this, but basically it's going to wind up pointing outwards here. Okay, and that's what we see with that clockwise rotation. Okay, all right. And of course, if we rotated these the other way, if we rotated this one clockwise, this one counterclockwise, you would see, your ethyl groups pointing in these directions, of course. All right, but in both cases, we see that disrotatory rotation. Okay, now if you ever have trouble remembering this, like I said, when in doubt, just quickly sketch out your molecular orbitals. Though again, if you want to memorize a rule to help you save some time on a quiz or exam, we have what are called the Woodward-Hoffman rules, because these depend on those outside two carbons and whether the p orbitals on those carbons are going to be in the same phase or opposite phases, and this is always determined by the number of p orbitals you have. You can kind of figure it out just based on the number of pi electrons you're dealing with. Right, so if you have 4 pi electrons, as we've seen with 2 double bonds, right, if you have 4 sp2 carbons there, under thermal conditions with just heat, it would be a conrotatory rotation, and if we put that in the excited state using light, it's going to be a disrotatory rotation. However, if we have 6 pi electrons, under thermal conditions, that's going to be disrotatory, and photochemical will be conrotatory. Okay, so if you want to memorize this as a rule, you can. But that being said, it's probably a little bit difficult to memorize because it's very easy to get these two mixed up. So if you don't want to do that, like I said, if you can just sketch out that molecular orbital diagram, and the more you practice it, the quicker and easier it becomes. And then that's kind of a foolproof way to figure out whether which way your orbitals are going to rotate to have those lobes of the same phase overlap. Finally, we have sigmatropic rearrangements. So again, with the sigmatropic rearrangement, if we break down that name, we're moving a sigma bond. And since this is a rearrangement, we're not changing the net number of bonds. We still have the same number of sigma and pi bonds in our reactant and product. All that's changing is that one of those sigma bonds is moved. So we're breaking and forming a sigma bond, in other words, overall. Okay. So here's an example of the of the molecule that we're using, right? So here we have a 1, 2, 3, 4, 5, 6. We have a hexadiene with double bonds at the 1 and 5 position. So it's 1,5-hexadiene here. And our product's still a 1,5-hexadiene. But you can see that the physical location of the bonds are different. Okay, and obviously if we have substituents, then obviously the reactant product will be, will not be identical molecules. All right, but that being said, in this generic example, you can see how this sigma bond is actually moved. Okay, please note that the pi bonds also move. We're still going through that cyclic transition state where pairs of electrons just rotate around. And again, we could draw this in either direction, but basically this sigma bond breaks and forms a pi bond here. This pi bond forms a sigma bond here, and this pi bond moves over here to form this pi bond. Okay. Now, when we look at our reactant, our product, and our transition state, it sometimes helps to number the carbons, and that helps us categorize the type of sigmatropic rearrangement we're looking at. Okay, so if we look at the bond that we're breaking and the bond that we're forming, and we count either side of those bonds, we count the carbons on either side of those, the number of carbons linking each of those, carbons from the bond we're breaking and the bond we're forming gives us the type of sigmatropic rearrangement. So you can see here we're breaking this bond here. So if we look at that top carbon and we look at the bond we're forming and we look at the top carbon there are 3 carbons involved, right? So we go from 1 to 3, okay, in that transition state. Likewise, for this carbon down here, there's 1, 2, 3 to get to the carbon over here where that bond is formed. Okay, and that's why this is called a 3,3 sigmatropic rearrangement. It's possible to have other types. So now over here we have a 1,5 sigmatropic rearrangement. So here again, if we look at our transition state, notice that we're breaking this carbon-hydrogen bond and we're forming the carbon-hydrogen bond over here. Okay, so if we look at one end of that transition state to the other end, okay, where we're forming that bond, there's 1, 2, 3, 4, 5 carbons, 5 bonds, 5 atoms in between those. Okay, likewise over here, there's only 1 atom involved, right? So that's why it's a 1,5 sigmatropic rearrangement. Okay. Again, even with these, there are different types of rearrangements, and it sometimes helps to know the names of these, just for quick and easy reference. So a Cope rearrangement is a common sigmatropic rearrangement you might see, where it's a 3,3 sigmatropic rearrangement involving carbons in the transition state. So your 6-membered ring, the 6 atoms involved in the mechanism are all carbons. Okay, it's possible to have substituents that are not carbons. In this case, we happen to have one that is a carbon, but you could have something that's not a carbon. The important thing, though, is that these 6 atoms here are carbons. Okay. Notice that for this particular example, this one's product favored. All right, so think about why that might be. Okay, so if you look at your double bonds, notice that this one's monosubstituted, this one's monosubstituted, right? Here's a carbon, there's a carbon. This double bond over here is still monosubstituted, but this one is disubstituted, right? We have a carbon here and a carbon here. So that's why this is more stable. Okay. Again, there's no way to sort of memorize this. You kind of have to like look at your product, look at your reactant, and make a judgment call there which one's more stable. So that's a Cope rearrangement, right? It's a 3,3 sigmatropic rearrangement involving only carbons. Another very common sigmatropic rearrangement you'll come across, a named one that you'll come across, is the Claisen rearrangement. Okay, so by the way, this you've probably come across this name in organic chemistry quite a bit. You have an adapter named after the same guy in your microkit and lab. Um, and depending on who you talk to, I find that most Americans pronounce this Claisen. They call it Claisen rearrangement or Claisen condenser. But I think the German way of pronouncing this, typically in German, when you have two vowels next to each other, you pronounce the second one. So this would be pronounced Kleisen in German. So depending on who you talk to, I feel like the proper way to pronounce this is Kleisen, but like I said, I know plenty of Americans who say Clayson instead, so um, you might come across it pronounced either way, so just be ready for that. Anyway, I went off on a tangent there. Claisen rearrangement is a 3-3 sigmatropic rearrangement as well. However, in this case, one of your atoms is going to be an oxygen. Okay, so here, notice that the oxygen's part of our molecule. It's sort of internal here, right? It's an ether functional group. When we do our rearrangement, we wind up with an aldehyde here. Okay, so we've got a carbonyl in this process, and this is again product favored, right? This carbonyl is much more stable. It's much more stable than having this ether functional group, right? And much more stable than these alkenes. Okay, so typically, the enthalpy of that bond formation kind of drives this forward. Okay. All right, so here's another example of this in just biochemistry. So when vitamin D is being produced, one of the steps involves a rearrangement. So here you can see electrocyclic ring opening, and then out of the resulting product, we see a 1,7 sigmatropic rearrangement here. You can actually see that. That hydrogen moving over here, right? So if you look at the transition state, this is the bond that we're forming, and this is the bond we're breaking. So that hydrogen is the only atom on the top of that transition state, and the bottom of it, we go 1, 2, 3, 4, 5, 6, 7 atoms to the bottom of that bond being formed. So it's a 1,7 sigmatropic rearrangement there. All right, so finally we come to UV vis spectroscopy. I've kind of highlighted in the last couple of chapters how important these characterization methods are for understanding or identifying particular functional groups or determining how things are linked together. UV vis spectroscopy is just very useful for these conjugated pi systems. It just happens that the energy gaps of these conjugated pi systems tend to match photons in the visible and ultraviolet range, right? So typically those photons will be somewhere in that UV vis range. Okay, just to jog your memories, I talked about this a little bit earlier, but that's basically what causes a ground state to excited state transition, right? When we shine light on this, and the energy of our photon matches the energy gap between our HOMO and LUMO, that energy will cause one of these electrons to get bumped up here, and what was previously the LUMO is now the new HOMO. Okay, so that pi bonding to pi antibonding interaction is essentially what we're measuring in UV vis spectroscopy, because those photons are in either the ultraviolet or visible region of the spectrum. Okay, so how does UV vis work? Basically, you take a beam of light, all right, so, and again, you know what the wavelength is, and therefore the energy is, or the instrument does at least, and it splits it into two into two smaller beams, right? And the detector kind of measures the two beams and compares them. Now, one of them is just, basically you have a sort of a control, right? You just have your solvent that you're using for whatever sample you're going to test, but instead of having an actual sample there, instead of having your solute dissolved in the solvent, it's just blank solvent, right? So that's kind of a control. In the other beam goes through an actual sample. So you have a your a solution of your sample of the chemical you're trying to analyze, and both of these are in separate cuvettes. They're little like cuboid shaped glass vials. Okay, and so the light that's otherwise equal is going through these two different cuvettes, and the detector, well, detects them and notices differences between them. Okay, by comparing the intensities of the light of the beam that's going through your control without any solute in it, and with just solvent, and comparing it to the beam that's gone through your sample, right, the thing you're analyzing, taking the log of that, we get a value for A, all right, for absorbance. And that is graphed versus the wavelength of the light that we're using. Okay, so this is kind of what our graph looks like. Okay, so we have A on our y-axis, and we have wavelength on our x-axis, and you can see that at a certain point we have what's called lambda max. This is where A drops down to, or goes to a maximum here, and so lambda max is the wavelength that causes this maximum absorption. Okay, and so that tells us essentially what the energy gap is for that transition. So the wavelength of this light, of these photons, must correspond to the energy of that gap. Okay, so based on the difference in wavelength, we can then figure out the difference in energy gaps for different systems. Okay, generally speaking, the larger your energy gap, the smaller your wavelength, and vice versa. Okay, so think back to where we talked about electromagnetic radiation, or think back to a physics class, right? E is equal to h nu, and nu is equal to c over lambda. So if I write that out, E is equal to h times c over lambda, which is wavelength. So in other words, your wavelength is inversely proportional to your energy. Okay, so the smaller the energy, the larger the wavelength, and vice versa. Okay, so you can see that this large energy gap has a lower lambda max. This small energy gap has a larger lambda max. Okay. Now, what affects the size of this energy gap? Well, one of the main ones that affects them is having a larger conjugated pi system. The more molecular orbitals you're trying to squeeze into the system, the more squeezed together and the smaller those gaps are. Okay. So that's kind of so one of the things we look at. We essentially start, if we were to predict the lambda max for a particular molecule, okay, what we call a chromophore, okay, a particular chromophore, we look at that, at our conjugated pi system, and we essentially start off with just a diene, right? And know that it's going to be a base value of around 217 nanometers. And then we're just going to go from there. Okay, so we look at how many, how far does this conjugated pi system get extended? So we add 30 nanometers for every extra pi bond. Okay, and then we also look for what are called oxochromes. In other words, substituents that are on this conjugated pi system. Okay, so you can see here, if we have two extra double bonds, we have to add 60. And so, we'd predict that instead of 217, we'd actually expect a lambda maximum around 277. Okay, now in real life, for this particular example, it winds up being near 290 instead. But again, this is a good way to make an estimate. Right? This is kind of like how we would estimate where, what our our ppms, our chemical shifts for our NMR peaks might be based on, what's attached to your methyl group or your methylene carbon or so on. Okay, so it's kind of a very similar process to predicting our lambda max. Okay, let's look at oxochromes. So for every additional alkyl group as an oxochrome that you have sticking off of your conjugated pi system, add 5 nanometers. So here you can see that we've got a diene, and there are 3 methyl groups. So for each of those methyl groups, we add 5 points, 5 nanometers, so that's 15 in total. That adds up to 232, which is actually what we'd observe for this particular molecule. Now, it's possible to have your diene as part of a ring, and depending on how it's part of that ring, that kind of will affect your lambda max accordingly. So, for example, let's say you have one of your double bonds exocyclic, in other words, sticking out of your ring. Okay, that would add 5 points or 5 nanometers to your lambda max. Okay, now of course, as part of this ring, don't forget you have 2 carbons coming off of your conjugated pi system, so you do have to take into account those 2 alkyl groups. So we add 5 nanometers for each of them. Okay, so again, we'd expect in this example here, we'd expect an extra 15 nanometers, which is relatively close again to what we'd observe. It's possible, of course, to have your diene stuck within a ring. Okay, so it's both of your double bonds are part of the ring. So notice that they're in this S-cis configuration. Okay, in doing so. So whenever they are done so, like whenever they're stuck in that S-cis conformation because it's part of a ring, they're both part of the ring, that actually adds 39 nanometers in, figuring out your math. All right. Now, of course, again, don't forget to include carbons attached to that system. In this case, there happen to be 4 of them, right? So if we have our pi system here, 1, 2, 3, 4 carbons, there's a carbon coming off this one, there's a carbon coming off this one, coming off this one, and coming off this one. So again, that's why there's 4 alkyl groups there for oxochromic groups. So that adds 20 nanometers right there. So if we combine that, we'd expect 276 nanometers. Okay. Again, it's not going to be perfect. These are just estimates, but it gives you a good idea of roughly where you'd expect your lambda max to be. Okay, so this accounts for color. So a lot of organic compounds aren't brightly colored. You notice that a lot of the solids we make in lab tend to just be like white crystalline solids. But when we do have colored compounds, organic compounds, this is where that color comes from. It's often these conjugated pi systems and their interaction with visible light that causes us to see color in these compounds. For example, lycopene, right? Lycopene is the pigment that's responsible for the red color you see in tomatoes. Okay, and if you look at lycopene, you can see that we have, of course, this huge conjugated pi system over here. All right, and that is that's what absorbs light, so that absorbs a particular part of visible light and causes the more red light to reach your eye and make the tomatoes appear to be red. Okay. Likewise, beta carotene makes carrots look orange. Again, notice this large conjugated pi system that will absorb light in such a way that you tend to get more orange photons reaching your eyes. Okay, so notice the way I phrase that statement, right? It's not so much that the molecules themselves give off the photons we're looking for. It's more that they absorb not the photons that we see. So you kind of see a sort of a complementary color system here. Basically, if you look at our color wheel, the color opposite what you observe is actually the color that's being absorbed. So beta carotene looks orange, but that's because it absorbs blue light. Okay, tomato lycopene looks red, but that's because it absorbs green light, and so on. Okay, um, it, since colored compounds, appear that way because of these conjugated pi systems, a quick way to interfere with this is to just break up that conjugated pi system. And this is basically how bleaching, bleach in general works to bleach things. Effectively, the bleach oxidizes bonds and opens up parts of these conjugated pi systems, and now you no longer have this extensive conjugated pi network. You just have smaller pockets that are isolated. And the thing is, then they absorb in regions that are not visible. They absorb more in, let's say, the UV range, for example. Um, and as a result, the because you're getting into shorter wavelengths and therefore higher energy. So you're going beyond the visible light into UV vis. So as a result, you can no longer see these compounds, right? So let's say you've got something that's causing a stain by breaking up the, um, you know, the long conjugated pi systems in there that make that stain visible to your eyes. Uh, you no longer make them visible to your eyes. However, okay, and this is the really interesting thing about this, those stains are still there. Those chemicals that originally caused, your eyes to see the absence of that light and therefore see that color, those chemicals are still present on the fabric, right? So you bleaching doesn't actually get rid of those. It just makes them invisible. This, by the way, is why if you spill mustard on your shirt and you clean it off, but then you go to a rave and under the black light you see like that stain still there, as you know, as I'm sure you all have at some point. That's where that comes from. Okay, that's why stains will show up under a black light, because instead of visible light being bouncing off your the fabric, bouncing off the stain, you now have UV light that does bounce off it and get absorbed, and therefore you notice the stain, or your eyes pick up that absorption of light. All right, so basically our eyes themselves work on this principle. In order to interact with photons, as basically as biological tissue containing organic molecules, the photosensitive cells in the retina of our eyes have to also have these conjugated pi systems in order to work. Okay, so going back to a little bit of biology, you may be familiar that the cells that you find on your retina are broken up into rods and cones, right? So if you remember, rods are really good at light sensing. So they can detect the presence and absence of light. They don't really help you much with color, but they just tell you like, okay, like they'll, if light hits them, they start firing, right? So typically, animals that have really good night vision will tend to have more rods. Okay, so like owls, for example, so nighttime predators in general are have several, like lots of rods in their eyes, okay, in their retinas. Cones, on the other hand, are important for the detection of color. Okay, so animals that are more active in the day, where nighttime vision isn't as important, tend to have more cones. You can see color that again helps you distinguish between different things a lot more easily. Okay, so a common light sensitive compound, the light sensitive compound that you'll find in the rods of your eye is rhodopsin. Okay, so retinal basically binds onto opsin, the protein opsin, and informs this rhodopsin. And notice again, we have that conjugated pi system in this molecule. Okay. Now, by the way, where do we get cis-retinol from? They always say that eating carrots is good for your vision, and that's because the beta carotene in your carrots, as well as vitamin A, can be converted into retinal. Okay, which of course is then necessary for rods functioning the way they do. So if you have a shortage of beta carotene or vitamin A, you tend to have what's called night blindness, right? You have trouble, seeing at night because the rods don't have enough retinal. All right. So how does this work? Essentially, when a photon of light hits the rhodopsin, basically the shape changes. That change in shape essentially just plays around with ion channels, which in turn causes a nerve impulse, and your brain makes sense of that nerve impulse. Okay. All right, and that's it for this chapter. So let's go through some practice problems and go from there. All right, so explain the relationship between heat of hydrogenation and stability of a pi system. Kind of talked about this earlier about just heats of reaction in general with the stability of molecules. When you look at potential energy, if something is more stable, it's at a lower potential energy. Well, if you hydrogenate to get the even more stable product, if it's at a lower potential energy, it doesn't have a lot of heat of hydrogenation, right? Because it has less to travel to drop down in energy. But if you have something that's particularly unstable, it would be at a higher potential energy, and its heat of hydration is higher. Okay, so that's the quick way to tell. If something has a higher heat of hydration, it's less stable than something with a lower heat. Okay. Explain why the instability of electrons in a pi molecular orbital directly relates to the number of nodes the orbital possesses. Again, I think these questions are very, kind of declarative. These probably aren't great practice for things you'd see on a quiz or an exam, which are a little bit more application based. But it's good to understand to do these just for knowing the background behind why the answers are what they are. So remember, you want overlap between orbitals. That's kind of where the you have stability arising from that. So with fewer nodes, you have more overlap between the orbitals, and therefore it's that that molecular orbital is more diffuse. Those electrons have more space to occupy, more positions to be found in, and and that again is really tied into stability. Here we have an application-based question. So here we have a conjugated diene, and notice that we are reacting this with HBr, so we're doing a hydrohalogenation. Okay, so like just a regular Markovnikov hydrohalogenation. Note that this is being done at 0 degrees Celsius, so a relatively low temperature. So ask yourself, what will your product be? Again, I don't recommend memorizing it's low temperature, it's going to be the 1,2 adduct or something like that. Try drawing out the cation you would form when a proton attacks one of these, adds on to one of these alkenes. Okay, so hopefully you should have gotten this. So if you add on a proton to this hydrogen, for example, notice that here we've got this tertiary carbocation. It's allelic as well. So if you look at the resonance structure here, you have this resonance structure where we've got a secondary carbocation. Okay. Note that we're doing this at a lower temperature, so we want the more stable intermediate. So that would be the tertiary carbocation here. And so that would give us, either one of these products. Please note this tertiary carbocation is flat, so the bromine can add to either side. So this chiral center, we have a chiral center here, and you'll get a racemic mixture of products. Okay, So here we have a Diels-Alder product. Notice that it's bicyclic, so that tells you that one of your, actually it looks like both of your reactants are going to be cyclic compounds, but anyway, I'll let you figure this out. So here's the actual Diels-Alder product. What are the diene and dienophile you'd get from a retro Diels-Alder? Okay, so in other words, what diene and dienophile would give you this product if you were thinking of this as a regular Diels-Alder? Okay, if you're having trouble seeing this, remember, look for that six-member transitions or that six-membered ring that has a double bond in it. So notice that here we happen to have a six-membered ring, and there's a double bond, which means that originally our diene had a double bond here and here, and these are the two pi bonds that, or the two sigma bonds that we formed in the process of this. So this was probably our diene. It was probably this five-membered heterocycle with an oxygen over there. And this was probably our dienophile. This was a double bond over here in this five-membered ring, and we had a substituent coming off of that carbon. This is our electron withdrawing group, by the way. That's also another marker that helps us identify where our dienophile is. Okay, so when we break those bonds, there's our two products. Okay, so again, if you're having trouble seeing this, you could try working backwards on this, or forwards, depending on how you look at it, right? If this is your diene and this is your dienophile, ask yourself, okay, if I do a Diels-Alder reaction between these, do I get this product? If so, then that's the right answer in multiple choice. Okay, let's look at our electrocyclic reaction. So here we have a ring. We're going to do a ring opening. Okay, so ask yourself, what will that product look like? Okay, again, it might be easier to think of this backwards, right? So think of, imagine that this bond over here was open, and you closed it to form this six-membered ring. Ask yourself, to get this stereochemistry with these six carbons. Okay, so again, think about the molecular orbitals you're dealing with here. To get this stereochemistry with those six carbons, was there a conrotatory or disrotatory rotation? Okay. So try drawing those out, and again, see if you've got a conrotatory or disrotatory rotation. Okay. So basically, if you try to draw this out. Okay, so let's say we break. If you're having trouble seeing this, basically we're breaking this bond over here, right? Okay, so out of our six carbons, how did this rotate to close this, right? Draw your molecular orbitals. 4, 5, 6, and again we're going to go this under heat, so our HOMO is going to be the third one up out of our six potential molecular orbitals. Okay, it's going to be midway, because the next three up that give you that complete your six molecular orbitals, those are going to be unoccupied. So since we're doing this under thermal conditions, they're not important. So again, lowest has these all completely filled. This has one node where these three are in the same phase and these three are in the same phase, but not with each other. And then this one has two nodes. So here's the important part. The outside two carbons are in the same phase, which means there's a disrotatory rotation when this closes to give us this product. Okay, so when this closed, that disrotatory rotation, formed this ring with these two methyl groups cis to each other, which means that if we were to open these up, okay, which would also be a disrotatory rotation, these two methyl groups would be pointing away from each other, or they could be pointing towards each other, depending on who you like to draw it. Here it looks like they've drawn them pointing away from each other. So this methyl group is pointing outwards, this methyl group is pointing outwards. which makes sense. Like if you do a disrotate rerotation, they're cis. In order for this metal group to be pointing outwards, though, this ethyl group has to be pointing inwards, and that's kind of how they've drawn this molecule here. Okay, and of course, if this is not very stable, so it's possible to draw this out in the in the S trans format. So again, look out for that. All right, and that's it for the practice problems. Again, like I said, only those last couple were really good practice problems for some of the more application type stuff that you'd like to see. So please do try out the the recommended homework problems. Look at the solutions manual to check your answers and make sure they make sense. And as always, if you get stuck or need any help, just let me know. And yeah, good luck with your quiz, and I'll catch you in the next chapter.